So, welcome to the second last lecture of this course. In the last lecture, we were discussing time temperature transformation diagrams as well as the continuously cooled transformation diagrams. So, we had seen how we can evolve the time temperature transformation diagram from the transformation kinetics, and we had then seen how we can transform the TTT or the time temperature transformation diagram to the CCT or the continuously cooled transformation diagrams. So, here is where we were in the last lecture, where these solid lines, the solid C curves are the TTT curves for a austenite to perlite transformation in a steel, and then we had used the principle of additivity to convert this TTT diagram to the CCT diagram, which is shown by these broken lines. So, here we had only done a very small part of the curve on a spreadsheet to show how this principle of additivity is used. Here now you see a larger part, that this broken line, for example, here shows 1% transformed if you have these continuously cooled curves for a sample. So, what this means is that if I am cooling along this path, at this point here we would have 1% perlite formed from austenite, and if you continue cooling, then at this point here we would end up with 99% cooled. In the last lecture I had not shown this line, but this line has also been now calculated using the same additivity principle. Similarly, you can look at this other cooling diagrams, but one of the things that I would like to impress on you, that when can this additivity principle be used? Whenever you have the rate of transformation can be related to as purely a function of the fraction transformed and as a function of the temperature. And then we had shown that if the transformation was following Avrami kinetics, then for this system n must be a constant. If n is not a constant, then that the validity of the principle of additivity is lost, and we cannot use that principle. Now, we had also talked about that n is a function of the mechanism of the transformation, and here we have the same mechanism of transformation throughout. So, it would be reasonable to assume that n is constant, and only the parameter k of the Avrami equation is a variable, and which is a function of temperature. Now, on this diagram, already in the earlier lectures you have been told that if you cool very fast, like on this curve, then you do not touch any of these curves, and hence no diffusional transformation is possible, and in steels you end up with a line which is called MS line, which is the martensitic start line. So, therefore, the austenite then directly transforms to martensite. Now, let us just follow each of these cooling curves, and we will use these broken lines as my CCT or the continuously cooled transformation curves. So, if I am following this particular line, which is a relatively low rate of cooling, so I will start forming perlite here, and by the time I reach this point, I would have completed almost all of the transformation, and all of austenite would have transformed to perlite. So, therefore, the end product would be perlite if I follow this. If I follow this particular curve, which is a somewhat faster rate of cooling. Again, when I reach this point, 1% transformation occurs, and by the time I reach this point, almost all of austenite has transformed to perlite. So then what is the difference between these two cooling curves? Does it make any difference to the microstructure? Because in both cases we are getting perlite. Well, yes, in both cases you get perlite, but in one case you will get a perlite which is relatively coarse, which means layers of ferrite and layers of cementite are going to be thicker as compared to the faster cooling rate followed by this path, where you would get a much finer perlite. So, if you want, so this now gives you a handle that you can now design a heat treatment where you may want to have a fine perlite. Why do you want a fine perlite? Well, having a fine scale microstructure, having a fine perlite gives you improved mechanical properties in terms of strength as well as ductility. That is why you may want to prefer fine perlite, and then you may want to do a faster cooling to get a fine perlite. Now, let us take a look at this third cooling rate. Now, here what happens is it touches this broken curve, broken line, which is the CCT curve. Well, this one, at this point 1% transformation starts to occur, and then as we go along some more transformation will keep occurring, but it never touches this 99%, it will never touch this 99% transformation curve, because this curve will end somewhere here. So, what would happen in this case? Well, part of the austenite will transform to fine perlite, and whatever is left when it hits the MS line, then it will undergo a martensitic transformation, and therefore, the final microstructure you will get would be a fine perlite plus martensite, which is as you know, is a very hard phase. So, this kind of a microstructure would give you properties which are very different from the properties when you get fine or coarse perlite. Now, let us look at this final fourth curve. Fourth cooling curve does not touch even the starting of the transformation or starting of the diffusional transformation, and it directly goes below the martensite start line. Hence, the final microstructure you will get would be 100% martensite. And if I just take this microstructure and use it in some application, it may not work out for me. Why it will not work out for me is that this would be an extremely brittle material, and you may then want to somewhat soften it by tempering it at maybe temperatures of 400, 450 degrees centigrade for some time, so that you get a tempered martensitic structure, which would be hard as well as a little bit of softness has been imparted to it by the tempering treatment. Now, with this thing that we now have in place the transformation diagrams, with these diagrams we can actually design different kind of heat treatments. But before I really go into the principle of heat treatment, I would like to introduce an interesting topic, an important topic, and which is called as hardenability of steel. And hardenability of steel is directly related to my transformation diagrams, as you will see shortly. So, let us try to understand what does hardenability of steel mean to us. So, hardenability of steel is the ability of steel to transform from austenite to martensite at a given depth when cooled under a given condition. What this essentially means is that if I take, let us say I take a round bar, I heat this up so that, heat it up in the austenitic region so that I have 100% austenite in the steel, and then I quench it in some quenching medium. So, what would happen? Very clearly, the surface regions of the steel, so in this region the cooling rate would be very fast. So, cooling is fast, while if I go right to the interior, depending on the dimension of the rod, the cooling will be relatively slow, and if this dimension is large enough, then cooling can be quite slow. So, in fact, you will have all along, right from center to the surface, I will have varying cooling rates. Now, imagine that I have a CCT diagram for this particular steel for a given composition. My CCT diagram may be something like this. This is the start line, this is the end line, this is the temperature and the time axis. Now, where the cooling is very fast, so I am here, let us say out here everything is austenite. On the surface, so this, if I call it as number 1, so this is number 1, that cooling in this surface region is so fast it does not touch any of these curves. Hence, I am going to get martensite here, which incidentally can be, we use the symbol alpha prime. At the center, my cooling may be something like this. So, this is, let us say, region 2 in the interior. Here, then I am going to get martensite plus ferrite plus pearlite. No, sorry, there will be no martensite, because it does not, martensite start line is here, it simply starts the transformation, pearlite starts to form and pearlite formation ends, and hence at the center I have only ferrite plus pearlite. Somewhere in between, if I call this as 0.3, my cooling could be something like this. Here what would happen is I will get ferrite, I will get pearlite, I will get partly martensite. So, I am going to get a mixed microstructure. Of martensite, ferrite plus pearlite. Of course, if I was looking at eutectoid steel, then I will only be getting pearlite or pearlite and martensite, or only martensite. Now, this, using this idea, we define what is called as the Grossman's hardenability. And in fact, before I even do this, let me just show you that this is the slide showing quenching of a round bar. So, I have martensitic structure at the surface, right in the center I have ferrite and pearlite, and in between I have ferrite, pearlite and martensite. Of course, if my cross section was very small, then I may not get such differences. So, now using this idea, we can determine what is called as the Grossman's hardenability. And what is Grossman's hardenability? Well, first of all, it uses cylindrical specimens of varying diameters. So, I will have several cylindrical samples of different diameters, and what I do, I austenitize them. So, first take it to the heated to austenite region. From the austenite region, you quench the samples. Then, if this is my sample, I take a section in the middle of the sample. So, I will have a section like this, and I look at the microstructure at the center. What is the microstructure here? What kind of a microstructure I have here? As expected, I should have either ferrite, pearlite, or I might have a mixture of ferrite, pearlite, martensite. If for a given diameter, so if for a given diameter the microstructure in the center has 50% martensite, if it has 50% martensite for a given diameter d, then this diameter is denoted as the critical diameter, and that is what defines the Grossman's hardenability, that for a given this particular diameter, I will get on quenching 50% martensite at the core of the sample. Now, this is also not very satisfactory, and I will just show you what is the problem with this definition, and then we will come up with a alternate definition of hardenability. So, what would D critical depend on? What factors would D critical depend on? Well, one is very clear, it will depend on composition of steel. So, that is all right in some senses, that D critical will tell me whether the steel has a high hardenability or a very low hardenability. In fact, what does it mean by high hardenability? High hardenability means that D critical will be large. Low hardenability means D critical would be small. So, for example, in what circumstances would D critical be large in terms of the composition of steel? Well, it depends on how the various alloying elements affect my transformation diagram. If on adding an alloying element, the CCT curves shift to the right, what this essentially means is that it is easy to cool without touching any of the diffusional curves, in any of the C curves. So, for instance, I have at some depth I have a cooling rate like this. If an alloying element shifts these diagram to the left, then for the same cooling rate I will start getting ferrite and pearlite. But for another steel where I have added some other alloying element which has shifted the cooling curves to the right, this may simply not touch the C curves and directly go below the martensite start temperature. So, those alloying elements which will shift these C curves to the right would mean that they would increase the hardenability of steel. And some of those alloying elements which would do that are, for example, chromium, molybdenum, manganese, silicon, nickel, vanadium. that these elements when added to steel shift the transformation diagram to the right and hence increases the hardenability. So, this in that sense D critical is a good measure for comparing for different steels, but this are all for a given quenching medium. Now, you can have other quenching medium which may produce different cooling rates and hence D critical would change. For example, if I do oil quench, now oil quench compared to water quench would be less severe and hence D critical would become small because these cooling rates are going to be relatively low. On the other hand, if I use water quench with agitation, then that would be much more severe than a plain quench in still water. So, then also then D critical would become different. So, in fact D critical would become larger. So, if we want to define hardenability in a way which becomes independent of the quenching medium, then Grossman hardenability, under Grossman hardenability, a concept called the ideal critical diameter was brought in. Now, what is this ideal critical diameter? This determines the hardenability independent of quenching medium. And this hardenability is defined as the diameter under condition of and what is called as an infinite quench. And what do I mean with that? What it means is that the temperature of the surface of the sample when it is quenched is brought down instantaneously in 0 time to the temperature of the quenching medium. And the diameter at which under this kind of a quench I get 50% martensite at the core of my round sample, the round bar, is called the ideal critical diameter. So, this is one way of assessing hardenability of steels of different compositions. Now, there is an alternate way and which is a widely used method of assessing hardenability of steels and which is called as the Dominie end quench hardenability test. And let us look at it. What does this Dominie test mean? How it is done? So, Dominie end quench hardenability test. The advantage of this kind of a test over the Grossman's hardenability is that you require one single specimen. In the Grossman's hardenability, you needed several samples of different diameters. Here we work with only one single sample, to assess the hardenability of a steel. So, that is one very big advantage. The other advantage of this is that it has very good reproducibility. Now, what kind of a sample do we use first? So, here is an example, here is a sample for the Dominie and Quench test. So, this is again a round bar. This is typically has a diameter of about 25 mm and a length of about 100 millimeters. And what do we do with this? Well, we take this sample of the particular steel for which you want to measure the hardenability, and you put it in a furnace to austenitize the sample, so that it is 100% austenite. Then you take it out of the furnace and very quickly put it in what is called as a Dominie apparatus. And in the Dominie apparatus, the sample is hung from the top and water is sprayed from the bottom, so that quenching is done at the end of the sample, and that is why it is called the Dominie and Quench test. So, the heat transfer takes place linearly in one dimensions along this path, and slowly the entire sample cools. So, what will happen is you will get different cooling rates. Fastest cooling will be near the end, and as we go away from the quench end, slower and slower cooling will take place. And it is best that I show you an actual video clip, so that it becomes clear what kind of a test is this. So, here this is in the lab. Out here you see that this is the sample which is being taken out of the furnace after austenitizing, and let me just play this clip. So, you quickly take this sample and put it inside this Dominie apparatus, and you can see now water is being sprayed from the bottom onto the sample, and slowly the whole sample is being cooled, but you would have different cooling rates. After the sample is completely cooled, you take it out and you can then section it at different distances from the end and look at the microstructure. Obviously, near the quench end you are going to get 100% martensite, very far away from the quench end you are going to get a ferrite perlite kind of structure, and in between you are going to get mixed microstructure. Steels with very high hardenability would have a very large depth up to which martensite would be forming, and steels with very low hardenability would form martensite in very shallow depth from the quench end. So, this very quickly one single sample enables you to assess the hardenability of steel. So, this I gave a quick idea regarding how to assess hardenability of steel, what is hardenability and how to assess hardenability of steel. With this, we close the lecture, and in the next lecture, we will look at some applications and some case studies where heat treatment principles are used.